A rolling element bearing, also known as a rolling bearing, is a bearing which carries a load by placing rolling elements between two bearing rings called races. The relative motion of the races causes the rolling elements to roll with very little rolling resistance and with little sliding. One of the earliest and best-known rolling element bearings are sets of logs laid on the ground with a large stone block on top. As the stone is pulled, the logs roll along the ground with little sliding friction. As each log comes out the back, it is moved to the front where the block then rolls onto it. It is possible to imitate such a bearing by placing several pens or pencils on a table and placing an item on top of them. See bearings. For more on the historical development of bearings, a rolling element rotary bearing uses a shaft in a much larger hole, and cylinders called rollers tightly fill the space between the shaft and hole. As the shaft turns, each roller acts as the logs in the above example. However, since the bearing is round, the rollers never fall out from under the load. Rolling element bearings have the advantage of a good trade-off between cost, size, weight, carrying capacity, durability, accuracy, friction, and so on. Other bearing designs are often better on one specific attribute, but worse in most other attributes. Although fluid bearings can sometimes simultaneously outperform on carrying capacity, durability, accuracy, friction, rotation rate, and sometimes cost. Only plain bearings are used as widely as rolling element bearings. Design. There are 5 types of rolling elements that are used in rolling element bearings: balls, cylindrical rollers, spherical rollers, tapered rollers, and needle rollers. Most rolling element bearings feature cages. The cages reduce friction, wear, and bind by preventing the elements from rubbing against each other. Caged roller bearings were invented by John Harrison in the mid-18th century as part of his work on chronometers. Typical rolling element bearings range in size from 10 mm diameter to a few meters diameter, and have load carrying capacity from a few tens of grams to many thousands of tons. Ball bearing. A particularly common kind of rolling element bearing is the ball bearing. The bearing has inner and outer races between which balls roll. Each race features a groove usually shaped so the ball fits slightly loose. Thus, in principle, the ball contacts each race across a very narrow area. However, a load on an infinitely small point would cause infinitely high contact pressure. In practice, the ball deforms slightly where it contacts each race, much as a tire flattens where it contacts the road. The race also yields slightly where each ball presses against it. Thus, the contact between ball and race is of finite size and has finite pressure. Note also that the deformed ball and race do not roll entirely smoothly because different parts of the ball are moving at different speeds as it rolls. Thus, there are opposing forces and sliding motions at each ball-race contact. Overall, these cause bearing drag. Roller bearings. Cylindrical roller. Common roller bearings use cylinders of slightly greater length than diameter. Roller bearings typically have higher load capacity than ball bearings, but a lower capacity and higher friction under loads perpendicular to the primary supported direction. If the inner and outer races are misaligned, the bearing capacity often drops quickly compared to either a ball bearing or a spherical roller bearing. Roller bearings are the earliest known type of rolling element bearing, dating back to at least 40 BC. Spherical roller bearings have an outer ring with an internal spherical shape. The rollers are thicker in the middle and thinner at the ends. Spherical roller bearings can thus accommodate both static and dynamic misalignment. However, spherical rollers are difficult to produce and thus expensive, and the bearings have higher friction than an ideal cylindrical or tapered roller bearing, since there will be a certain amount of sliding between rolling elements and rings. Gear bearing is roller bearing combining two epicyclical gear. Each element of it is represented by concentric alternation of rollers and gear wheels with equality of roller diameter to gear wheel pitch diameter. The widths of conjugated rollers and gear wheels in pairs are the same. The engagement is herringbone with the skew end faces to realize efficient rolling axial contact. The downside to this bearing is manufacturing complexity. Gear bearings could be used, for example, as efficient rotary suspension, kinematically simplified planetary gear mechanism in measuring instruments and watches. Tapered roller bearings use conical rollers that run on conical races. Most roller bearings only take radial or axial loads, but tapered roller bearings support both radial and axial loads, and generally can carry higher loads than ball bearings due to greater contact area. Tapered roller bearings are used, for example, as the wheel bearings of most wheeled land vehicles. The downsides to this bearing is that due to manufacturing complexities, tapered roller bearings are usually more expensive than ball bearings, and additionally under heavy loads the tapered roller is like a wedge, and bearing loads tend to try to eject the roller. The force from the collar which keeps the roller in the bearing adds to bearing friction compared to ball bearings. Needle roller bearings use very long and thin cylinders. Often the ends of the rollers taper to points, and these are used to keep the rollers captive. Or they may be hemispherical and not captive but held by the shaft itself or a similar arrangement. Since the rollers are thin, the outside diameter of the bearing is only slightly larger than the hole in the middle. However, the small diameter rollers must bend sharply where they contact the races, and thus the bearing fatigues relatively quickly. Carb toroidal roller bearings. Carb bearings are toroidal roller bearings and similar to spherical roller bearings, but can accommodate both angular misalignment and also axial displacement. Compared to a spherical roller bearing, the radius of curvature is longer than a spherical radius would be, making them an intermediate form between spherical and cylindrical rollers. The limitation is that, like a cylindrical roller, they do not locate axially. Carb bearings are typically used in pairs with a locating bearing, such as a spherical roller bearing. This non-locating bearing can be an advantage, as it can be used to allow a shaft and a housing to undergo thermal expansion independently. Toroidal roller bearings were introduced in 1995 by SKF as carb bearings. The inventor behind the bearing was the engineer Magnus Källström. Configurations. The configuration of the races determine the types of motions and loads that a bearing can best support. A given configuration can serve multiple of the following types of loading. Thrust loadings. Thrust bearings are used to support axial loads, such as vertical shafts. Common designs are thrust ball bearings, spherical roller thrust bearings, tapered roller thrust bearings, or cylindrical roller thrust bearings. Also non-rolling element bearings such as hydrostatic and magnetic bearings see some use where particularly heavy loads or low friction is needed. Radial loadings. Rolling element bearings are often used for axles due to the low rolling friction. For light loads, such as bicycles, ball bearings are often used. For heavy loads and where the loads can greatly change during cornering, such as cars and trucks, tapered rolling bearings are used. Linear motion roller element bearings are typically designed for either shaft or flat surfaces. Flat surface bearings often consist of rollers and are mounted in a cage, which is then placed between the two flat surfaces. A common example is draw support hardware. Roller element bearing for a shaft use bearing balls in a groove designed to recirculate them from one end to the other as the bearing moves. As such, they're called linear ball bearings or recirculating bearings. Constraints and trade-offs. All parts of a bearing are subject to many design constraints. For example, the inner and outer races are often complex shapes, making them difficult to manufacture. Balls and rollers, though simpler in shape, have small, since they bend sharply where they run on the races. The bearings are prone to fatigue. The loads within a bearing assembly are also affected by the speed of operation. Rolling element bearings may spin over 100,000 revolutions per minute, and the principal load in such a bearing may be momentum rather than the applied load. Smaller rolling elements are lighter and thus have less momentum, but smaller elements also bend more sharply where they contact the race, causing them to fail more rapidly from fatigue. Maximum rolling element bearing speeds are often specified in NDM, which is the product of the mean diameter and the maximum RPM. For angular contact bearings, NDMs over 2.1 million have been found to be reliable in high-performance rocketry applications. There are also many material issues. A harder material may be more durable against abrasion but more likely to suffer fatigue fracture, so the material varies with the application. And while steel is most common for rolling element bearings, plastics, glass, and ceramics are all in common use. A small defect in the material is often responsible for bearing failure. One of the biggest improvements in the life of common bearings during the second half of the 20th century was the use of more homogeneous materials, rather than better materials or lubricants. Lubricant properties vary with temperature and load, so the best lubricant varies with application. Although bearings tend to wear out with use, designers can make trade-offs of bearing size and cost versus lifetime. A bearing can last indefinitely, longer than the rest of the machine, if it is kept cool, clean, lubricated, is run within the rated load, and if the bearing materials are sufficiently free of microscopic defects. Note that cooling, lubrication, and sealing are thus important parts of the bearing design. The needed bearing lifetime also varies with the application. For example, Tadrike Harris reports in his rolling bearing analysis on an oxygen pump bearing in the U.S. Space Shuttle which could not be adequately isolated from the liquid oxygen being pumped. All lubricants reacted with the oxygen, leading to fires and other failures. The solution was to lubricate the bearing with the oxygen. Although liquid oxygen is a poor lubricant, it was adequate, since the service life of the pump was just a few hours. The operating environment and service needs are also important design considerations. Some bearing assemblies require routine addition of lubricants, while others are factory seal, requiring no further maintenance for the life of the mechanical assembly. Although seals are appealing, they increase friction, and in a permanently sealed bearing the lubricant may become contaminated by hard particles, such as steel chips from the racer bearing, sand, or grit that gets past the seal. Contamination in the lubricant is abrasive and greatly reduces the operating life of the bearing assembly. Another major cause of bearing failure is the presence of water in the lubrication oil. Online water-in-oil monitors have been introduced in recent years to monitor the effects of both particles and the presence of water in oil and the combined effect. Designation. Metric rolling element bearings have alphanumerical designations, defined by ISO 15, to define all of the physical parameters. The main designation is a 7-digit number with optional alphanumeric digits before or after to define additional parameters. Here the digits will be defined as 7,654,321. Any zeros to the left of the last defined digit are not printed, e.g. a designation of 0007-208 is printed 7208. Digits 1 and 2 together are used to define the inner diameter, or bore diameter, of the bearing. For diameters between 20 and 495 mm inclusive, the designation is multiplied by 5 to give the ID, e.g. designation 08 is a 40 mm ID. For inner diameters less than 20, the following designations are used: 00 equals 10 mm ID, 01 equals 12 mm ID, 02 equals 15 mm ID, and 03 equals 17 mm ID. The third digit defines the diameter series, which defines the outer diameter. The diameter series, defined in ascending order, is 0, 8, 9, 1, 7, 2, 3, 4, 5, 6. The fourth digit defines the type of bearing: 0. Ball radial single row 1. Ball radial spherical double row 2. Roller radial with short cylindrical rollers 3. Roller radial spherical double row 4. Roller needle with long cylindrical rollers 5. Roller radial with spiral rollers 6. Ball radial thrust single row 7. Heavy vehicle bearings prepared 7. Roller tapered 8. Ball thrust radial 9. Roller thruster thrust radial. The fifth and sixth digit define structural modifications to the bearing. For example, on radial thrust bearings the digits define the contact angle, or the presence of seals on any bearing type. The seventh digit defines the width series, or thickness, of the bearing. The width series, defined from lightest to heaviest, is 7, 8, 9, 0, 1, 2, 3, 4. The third digit and the seventh digit define the dimensional series of the bearing. There are 4 optional prefix characters, here defined as A321XXXXXX, which are separated from the main designation with a dash. The first character, A, is the bearing class, which is defined in ascending order, C, B, A. The class defines extra requirements for vibration, deviations in shape, the rolling surface tolerances, and other parameters that are not defined by designation character. The second character is the frictional moment, which is defined in ascending order by a number 1 to 9. The third character is the radial clearance, which is normally defined by a number between 0 and 9 in ascending order. However, for radial thrust bearings it is defined by a number between 1 and 3 inclusive. The fourth character is the accuracy ratings, which normally are in ascending order: 0, 6x, 6, 5, 4, t, and 2. Ratings 0 and 6 are the most common. Ratings 5 and 4 are used in high-speed applications, and rating 2 is used in gyroscopes. For tapered bearings, the values are in ascending order: 0, n, and x, where 0 is 0, n is normal, and x is 6x. There are 5 optional characters that can be defined after the main designation: A, E, P, C, and T. These are tacked directly onto the end of the main designation. Unlike the prefix, not all of the designations must be defined. A indicates an increased dynamic load rating. E indicates the use of a plastic cage. P indicates that heat-resistant steel are used. C indicates the type of lubricant used. T indicates the degree to which the bearing components have been tempered. While manufacturers follow ISO 15 for part number designations on some of the products, it is common for them to implement proprietary part number systems that do not correlate to ISO 15.